This is Unit 2. It's work, and specifically it's mechanical systems or mechanical work. And we're going to be looking at linear work today. That's going to be our area. All right, but let's take a look at mechanical work in general. All right, we have two categories of work. We have linear and we have rotational. Okay, linear force or torque. Torque is the rotational, and then linear is for the one we're going to look at today. Now, the difference between the two, when you see the word linear, all right, you see the word line right here. All right, that means that everything has to be in the same line. That if you're going to apply a force, it's in the same line or direction that the object is going to move. Okay, so if you push a cart, all right, you're applying a force horizontally, the cart's going to move horizontally. Now, torque is what I would call a rotational word, and you see an example here. We have a fan. So anything that's going to be turning in a circle is going to be torque. Okay, so if you want to talk about a wheel or a flywheel, you want to talk about a pulley, all of those would be in the category of rotational force. But we're going to zoom in on more specifically just linear today. And linear is actually it's fairly easy. Okay, so some things that we already talked about. Linear mechanical work. It is work. All right, now you might say, well, I don't know what work is. Well, work is going to be, I always think of it in the technical sense. It is force times the distance. All right, and it's like what I had said to you before. For you to do work, you're applying a force in the same plane. In other words, if you're applying a force horizontally, the object is moving horizontally. If you are lifting books off a shelf, all right, the force that you are applying is downward, or if you're putting them up there, upward. All right, and that's the direction that they're moving. Okay. Now, if you say, "Oh, I worked so hard today. I was studying, for this class that I have," that's not considered work. There are a lot of words in science that are misused, that in everyday life we don't use them in the scientific sense. So I say, "Oh, I worked so hard, I have a headache." That is not considered work. You actually have to apply a force, and it actually has to move. You lean up against the wall. You say, "Oh, I'm applying a force, I'm doing work." No, it hasn't moved a distance. If you can't measure it, it hasn't moved a distance. Okay, so just to look at a few things that we have here. It's going to be in a straight line. So you see I got this guy here, pushing. It's force times distance. Work is W, force is capital F, and D is distance. And here they're applying a force to a button. All right. They're applying the force down, the button is going down. Here you have a car. They're pushing the car, all right, in that direction. That's the direction that the car is going to move. So that's linear mechanical work. Okay, let's look at units. You're going to see that they're rather similar. In the English, all right, work is going to be foot-pounds. And how do we get that? Well, it's force times distance, so it's going to be pounds times feet. And to differentiate here, they like to say foot-pounds. Okay. And for the SI, it's Newton meters. Your forces are measured in newtons, and your distance is measured in meters. Now, does this mean, you can't use centimeters? Yeah, you can have a Newton centimeter, but the thing is, you usually want to have it in the meters, because what you're going to find out later on is that a Newton meter is actually equal to a new unit, which is called a joule. It's capital J. So that's why you like to keep them standard, because what happens is they can become another unit. All right. Okay, here's an example here. We have a weightlifter, and he's applying a vertical force. Okay, vertical force to raise a 200-pound barbell 5 feet. How much mechanical work is done in lifting the barbell? Well, you have to apply at least 200 pounds of force to raise that barbell. So this is going to be your force. And you are lifting it 5 feet. So that's going to be your distance. So what do? You've got work equals force times distance. That's going to be 200 pounds. That's your force. Your distance is 5 feet. You multiply these two together. And look, you get 200 times 5 will give you 1,000. When you multiply your units together, you get foot-pounds. So your answer there is the weightlifter has to apply at least 1,000 foot-pounds to lift that barbell 5 feet. Okay, when you start talking about work, you can't help but talk about the word efficiency. And, you start getting into machines. And efficiency basically is a way of explaining how well something works. All right, but we have such a thing as called friction. All right, and if you rub your hands together, all right, and they get warm, okay, that's actually friction. You're feeling the results of friction. So whenever you have anything rubbing on something, you're going to get friction. And because of that, you never, in real life, you don't have 100% efficiency. Okay, you do not have 100% efficiency. Now, sometimes in the theoretical problems that we look at, we're going to pretend that we have 100% efficiency, but the reality is we do not. Now, how do you figure that out? Well, what you're going to do is for percent efficiency, that's usually the terminology that we use, you're going to take output work divided by input work times 100. The 100 is supposed to take care so that you can use this percent. Now, what about these two terms, output work and input work? It's exactly what the words are telling you. The output work is what you're getting out. All right? The input is what you're putting in. Okay? And you always have to put more in than you ever get out because you also have to overcome friction. And what happens when you have friction, then you get other things occurring as well. It's kind of like a domino effect. You have parts that are rubbing on each other, and as they rub on each other, they get warm, and they start to expand, and those kind of things. And that's why you have to have other systems such as your oil and your radiator to take away that heat. And since you've got those, and the fan has to go for the radiator, it just can't, it snowballs. Okay? Anyway, the output is what you get out. The input is what you have to put in. And like I said, the input should always be bigger. Alright, so let's take a look at this problem. Alright, we have a block and tackle. Now, if you're not familiar with the block and tackle, a block and tackle has actually a series of pulleys in it and gears. And what it's used basically for is to lift heavy items. In this case, we're going to lift an engine. Alright, the engine weighs 600 pounds. Alright, and it needs to be raised 0.9 feet. Alright, so it's 600 pounds, 0.9 feet. I don't think there's too many of us that could, grab a hold of that engine by ourselves and lift it 0.9 feet. Okay, and if you had a whole bunch of friends, well, yeah, they could do that for you. But if you're by yourself, how are you going to do it? All right, you do not possess the ability to lift the 600 pounds, 0.9 feet. So you have to use a machine. And this machine, all right, basically what it's going to do, this block and tackle, all right, it is going to change so that you have to apply 100 pounds of force instead of 600. But what's the trade-off? There is always a trade-off. All right, you get nothing for free. All right, the trade-off is instead of moving it 0.9 feet, you're going to have to move it a whole 6 feet. You see the trade-off there? If we're going to go less force, you got to go greater distance. Okay, and this is what I was talking to you before about. Your input versus your output. You got to put more in. All right, to do the lifting of this engine. So let's take a look. All right, so the output force is what do we need done? The engine needs to be lifted 0.9 feet. So that's my output. All right. It doesn't matter. When you're looking at output, think of it in terms of this. What has to happen? Even before you decide what machine you're going to use, what has to happen? That 600-pound engine needs to be lifted 0.9 feet. So you're going to take your force times your distance, 600 pounds times 0.9 feet, and you're going to get 540 foot-pounds. That's your output. Okay, well, what about your input? This is what you have to put in. And remember, there's that trade-off here. Still going to use the same equation. Work equals force times distance. So, with using the block and tackle, you're going to use 100 pounds of force. But the distance that you have to move, usually with the block and tackle, there's a chain, all right, on there. So you're going to have to move that chain 6 feet. So look here, 100 pounds times 6 feet is going to give you 600 foot-pounds. See what I was telling you about how much you've got to put more in than you ever get out, because you have to overcome friction. So what is the efficiency? How do you work that? We have the equation that we were using before. And let's put that in there. The 540 is your output. The 600, all right, foot-pounds is your input. You're going to divide those. You're going to get a decimal, 0.9. And then you're going to multiply by 100. And you get 90%. That's actually pretty high. 90% is pretty high. I think a real block and tackle probably would be a much smaller efficiency. There are things like, for example, when you start looking at machines like, for example, a pump. Now, a pump, all right, it has a fan inside, all right, so that has to rotate. So you've got the friction of that rotating fan, or it's almost like a propeller, all right, to push the water through. And you have friction of the water in the walls of the tubes and through the pump. And you have, it's an electric motor. So when you have something that's electrical, it's going to get warm. And so as it gets warmer, all right, or the friction, it causes more heat to be added to the pump, and it just kind of snowballs, because what happens is it's the domino effect. As the the fan goes round, you get more heat. And as it's turned on, all right, the electricity, you get more heat. And the more heat you get, the more resistance you have in the pump, so you get more electrical heat. And you've got your resistance of your water against the pump and the tubing or the piping. So it just goes on and on. So that's why a lot of times they're only like 6% efficient. Okay, well, that wraps up talking about linear work, and next time we'll talk about rotational work. Have a good week.